So this is part 3 of module 3, where we're going to do an example lecture and an example video where we're just going to focus on examples, and we're going to be looking at examples of polytropic processes. So we ended part 2 with an example using steam and using our tables. Now we're going to switch our focus to looking at polytropic processes and how we can solve problems using polytropic processes and without necessarily using tables, but rather using the ideal gas equation. So the first problem that we have is written out already. It's also in your handouts, so you can use your handouts or you can follow along this lecture. But we have that argon is compressed in a polytropic process with N is equal to 1.2. And we're told that it's compressed from 120 kilopascals and 30 degrees Celsius to 1,200 kilopascals in a piston cylinder device. So we know we have a piston cylinder device, and we know that a compression is occurring. So we have some sort of compression where the piston cylinder is moving down. And we're asked to determine the final temperature of argon. So very simple question. We don't have to find the work. We're just trying to determine the final temperature of argon. The first thing we're going to write down is we're just going to underline the important things. So we know that it's argon. We know that it's a polytropic process. We know that N is equal to 1.2. And we're given the initial pressure and temperature. And we're given the second pressure, but not the temperature itself. So some of the assumptions that we're going to make in this question. Okay, so we have argon in here. Some of the assumptions that we're going to make in the question are that we're going to be using ideal gas. We know that argon is a gas, and we're going to assume that we have an ideal gas. Okay, we're not told anything else in terms of if we can use ideal gas or not. We could check if we can use ideal gas using our compressibility factor, but in this case we're just going to assume ideal gas because we don't have any extra information. We also can assume that we have absolute pressure. Okay, that's not always an assumption that we make, but we can say that we have absolute pressure. So we're not told that anything is gauge pressure, we're told the pressure, so we're going to assume absolute pressure. And obviously from the question we know it's a polytropic process. And finally, we also do not know the volume. So we're not told the volume. So how do we go about solving this problem? Well, let's write our state 1 and state 2. We know that argon is compressed from a certain state to another. So let's write state 1 and state 2 and the information we're given from the question. So state 1, we're told that P1 is equal to 120 kilopascals and temperature 1 is equal to 303 Kelvin. And state 2, we're told that P2 is equal to 1,200 kilopascals and temperature 2 is unknown, and that's what we're looking for. Now, what we're going to be doing in this lecture with the examples is we're going to be developing a little bit of extra theory and some shortcuts as well. So through the examples, we're going to learn a little bit more about how to solve a polytropic problem. So my first question is can we assume that the volume is the same between state 1 and state 2? And the answer is no, right? We have a piston cylinder assembly that has a gas in it, so the gas can move and the piston cylinder assembly, the piston moves, okay? The piston within the cylinder moves. Now, if we had a liquid and it was fully liquid, then maybe we could assume volume would be the same. But in this case, we just can't assume that. Okay? And so we have two governing equations for our problem. We have the first governing equation that says that from the polytropic process, PV to the n is equal to a constant. Okay, we know that from our derivation, and we know that that's what polytropic process means. And we have a second equation that we're going to be able to use due to the fact that we assumed that it was an ideal gas. So we can use that PV is equal to MRT. Now, we don't have the volume and we don't have the mass of the gas. So we're probably not going to be using this form of the equation. So what we're actually going to be doing is we're going to rearrange this equation to say that PV over M, so bringing the M to the left side, is equal to RT. And we know that V over M is specific volume. So we have PV2 we have PV2 is equal to RT. And I don't know why I put V2. It should just be PV is equal to RT. Okay, so we have these two equations to sort of govern what is happening to our problem. Now, how do we go about solving this problem? What are the steps to solve the problem? So, one way to solve the problem is to say, okay, we have these two equations. We have PV to the n is equal to constant, and we have PV is equal to RT. And we know from our equations that ideal gas is always respected and P1 V1 to the n is always a constant. So we can say that P1 V1 to the n is equal to P2 V2 to the n. And we can also write everything in specific format. So we can change it to specific volume. We can say, instead of using volume, we can say that P1 little v1 to the n is equal to P2 little v2 to the n. These statements are equivalent because the mass is the same in our system. The mass stays constant within our system. And so this is our first equation. This is equation 1. And we can also write that P1 V1 is equal to RT1 and P2 V2 is equal to RT2 from ideal gas. So this would be from ideal gas. Okay, ideal gas is respected throughout. So we have two equations essentially with three unknowns in each. Now, what we can do now in a second instance is we can take this equation and rearrange it. And we can say that P2 over P1 is equal to V1 over V2 to the power of n. Okay, so we can rearrange the equation, bring the V1 to the n on the right side, and bring P1 to the left side, and we get P2 over P1 is equal to V1 over V2 to the n. Okay, now from our ideal gas law, we can now say that we can rearrange it to substitute for this and this. Right? We do not have V1 and V2. So we can't use this equation to solve anything. And we're trying to solve for temperature. This equation doesn't have temperature in it. So let's rearrange our ideal gas equations to solve for V1 and V2. So V1 would be equal to R T1 over P1, and V2 would be equal to R T2 over P2. And now we have the following equation. We have that P2 over P1 is equal to R T1 over P1 divided by R T2 over P2 to the power of n. And you can see that the r's are going to cancel. Okay, the top and bottom r are the same value, so they're going to cancel. So we move forward and we say that P2 over P1 is equal to T1 multiplied by P2 divided by T2 multiplied by P1. Okay, we're just using rules of divisions within divisions, and we can simplify to this term right here, still to the power of n. And when something is to the power of n, we can separate the bracket and sort of bring it together if we want to. So we can say that this is equal to P2 over P1 to the n multiplied by T1 over T2 to the n from our power, from our mathematical manipulations that we can do with powers. So we now have that P2 over P1 is equal to P2 over P1 to the n and T1 over T2. So what we can do now is we can actually bring this over to the left side and then bring this power over to the left side as well. Okay, so we're going to rearrange the equation so that we're left with T1 over T2 on the right side. And that's it. Because we're trying to solve for temperature, right? Our goal is to solve for temperature 2. We have P2, we have P1, and we have T1. We need to find T2. So let's try and rearrange it to find something for T2. So on the right side, we would be left with T1 over T2. And on the left side, we now have P2 over P1. So we have P2 over P1 to the power of 1 minus n. Okay, this can be thought of P2 over P1 to the power of 1. So it's 1 minus n, and then when you bring a power from the right side to the left side, you divide everything by n. So now we have T1 over T2 is equal to P2 over P1 to the power of 1 minus n over n. And we can go one step further and rearrange this equation so that we have T2 on the top, just so it makes it easier. T2 on the top is equal to P2 over P1 to the power of n minus 1 over n. Okay, so the difference here is that this was rearranged. Okay, this term right here was rearranged. Okay, just making sure that we see that they were flipped because we now flipped our equation. Okay, so again, a little bit of a mathematical tool to modify our equation and to flip T1 and T2. It makes it easier to solve for T2 and not having to rearrange a bunch of stuff. So now we have this equation that is our final equation. And this equation is actually called an isentropic relation. And we'll be looking at that later on in the semester. But this is something good to remember. So it's an isentropic relation. And you can use these isentropic relations to solve for our polytropic processes very, very fast, essentially. So instead of having to derive this whole formula, you could just remember that for a polytropic process, you can use this shortcut. So for a polytropic process, with n is not equal to 1, you can use this shortcut. So instead of having to do this whole derivation, you could just use this equation to find T2. So let's use the equation to find T2. We can say that T2 is equal to T1 times P2 over P1 multiplied by, to the power, of n minus 1 over n is equal to 303. And notice how the temperature is in Kelvin now. Okay, so I made the temperature in Kelvin 303 times 1200 over 120 to the power of 0.2 over 1.2. And we get that our final temperature is equal to 445 Kelvin. And you can leave it in Kelvin if you want to, that's not a problem at all. Okay, so hopefully this example makes sense. And what we did through this example is derive from our ideal gas and our polytropic equation. We were able to combine both equations to solve for temperature in terms of pressure. Okay, so a little bit of a derivation. And you can start with your polytropic equation and your ideal gas equation every single time, and you will get the right answer. Another way to do this is you can use a shortcut, which would be to memorize this equation and just use it for polytropic processes. That would be fine as well. Okay, so let's do a second example now, which is going to be slightly different. And let me copy over the example from our handout. Okay, so this next example says, during some actual expansion and compression processes in piston cylinder devices, the gases have been observed to satisfy the relationship PV to the N is equal to C. So we're told that experiments have been done and people have seen that in piston cylinder devices, gases have been observed to satisfy the relationship PV to the N is equal to C. Okay, that looks a little bit familiar, right? And it tells us that N and C are constants. And based on this, it says to calculate the work done when a gas expands from 350 and 0.03 meters cubed to a final volume of 0.2 meters cubed. So for a case where N is equal to 1.5. So we're told that N is equal to 1.5, and we now have a state 1. So I'm going to write my states as always. State 1 is pressure 1 is equal to 350 kilopascals. Volume 1 is equal to 0.03. This is the actual volume, not a specific volume. And we're told that at state 2, we now have volume 2 is equal to 0.2 meters cubed. And what we're trying to find is work boundary. So we're trying to find work boundary. And work boundary, if we remember correctly, is the integral from 1 to 2 of PdV. And since our N is not equal to 1, we can use our first equation that we had written out, which was P2 V2 minus P1 V1 in our theory over 1 minus N. Okay, that's the equation for N is not equal to 1. So some of the assumptions that we're going to make in this problem, just as in the previous one. So in this problem, we're not told that we have a polytropic process, right? We're just told that it follows a relationship PV to the N equals C. We should be able to recognize that this is a polytropic process. And the second assumption is that we're going to treat this gas as an ideal gas. Okay, this is just going to be an assumption. Now from here, we just have to solve for the problem. So we have a couple of different terms. We have volume 1, we have pressure 1, we have volume 2 in our state 1 and state 2. We also have N. So the only thing we're looking for is pressure 2. How are we going to find pressure 2? So try to think about it for a second. How are we going to find pressure 2? So one way to find pressure 2 very easily is to use the polytropic equation. And we can say that our polytropic equation is just equal to P1 V1 to the N is equal to P2 V2 to the N. right? It is equal to a constant, so at point 1 and point 2, these should be equal. And we have all the terms except for P2 available. So we can rearrange this equation as P2 over P1 is equal to V1 over V2 to the n. Okay, and this is another shortcut equation that we can use to solve for this problem with the polytropic process. I like to always start from the basics just to derive everything, but you can use this shortcut equation, and this is another isentropic relation that we'll look at later in the class. But you can use this as a shortcut if you want to. And now we can just solve for pressure 2. So pressure 2 is equal to pressure 1, which would be 350, multiplied by 0.03 over 0.2 to the power of 1.5. Okay, very simple. And we get that our value for pressure 2 is equal to 20.33 kilopascals. Okay, now that we have our pressure 2, we now have all the terms in our above equation, and we can find work boundary. So work boundary would be equal to 20.33 multiplied by 0.2 minus 350 multiplied by 0.03. And make sure you keep the signs correct and you're not changing any signs, times 1 minus 1.5. Okay, and we get a value of, I'm going to write the value in white, of 12.9 kilojoules. And again, the answer is in kilojoules because we're using kilopascals for pressure. If you use pascals for pressure, your answer is in joules. If you use kilopascals, which is usually the preferred method, you would get kilojoules. So this means that the work was positive. And what that means is that the work was done by the system. And what work by the system means is that we have some work output. Our piston cylinder assembly, our piston is moving up. So if we were to draw the process on a PV diagram, this is extra to the problem, but just to draw it, if we had our PV diagram, we would have point 1 somewhere here, which would be at 350 pressure, and our volume 1 would be equal to 0.03. And then our second point would be 20.33, and our volume would be 0.2. So 0.2 would be somewhere here. And you would have a line that follows a polytropic process type of equation between 1 and 2. Okay? And 0.2 should be a little bit lower, but the diagram is not to scale. Okay. So that solves our second example problem. So let's look at another example problem. Let's copy over the next example problem in our handout. And we'll work on that next. Okay, so the next problem says a frictionless piston cylinder contains 5 kilograms of nitrogen at 100 kilopascals and 250 kelvins. So this is definitely state 1. Okay, we're given state 1 right here. Nitrogen is now compressed slowly, so now we have nitrogen starting to compress according to the relation of PV to the 1.4 is equal to a constant. And we're told it reaches a final temperature of 450 Kelvin. Okay, so we have, the first thing we can do is we can make an assumption because we have PV to the 1.4 is equal to a constant. We can say that the two assumptions we have, the first one is ideal gas, and the second one is we have a polytropic process. We recognize it as a polytropic process with N is equal to 1.4. Okay, and we're also told to calculate the work input. So now we don't have a work output, but we have a work input. So in the same way as before, the work input is just going to be the negative of the work boundary. Okay, so work input would just be equal to the negative of WB. Okay, and it really doesn't matter which way you do it. I like to leave it as just work boundary. Okay, so we're just going to find, in this problem, we're just going to find work boundary. And then from there, you can infer what the work input would be. It would just be the negative of that. Okay, and since we know we have a compression, we are expecting our work boundary to be negative. Therefore, our work input would be positive. Okay, so this is just a way of seeing, but essentially work input means that work boundary will be negative. Okay, and you can just find the work boundary. That's completely fine for me. And in any exam problem, you would be asked to find the work boundary, not anything else. Okay, so let's write our state 1 and state 2. So let me write it in white. State 1 is we have mass is equal to 5 kilograms of nitrogen. We're also told that pressure 1 is equal to 100 kilopascals. And temperature 1 is equal to 250 Kelvin. Okay, we're also told that at state 2, our mass is still going to be the same. So again, we're not told that it escapes or anything like that, and we're told it's in a piston cylinder device. So mass 2 is just equal to mass 1. And we're given that temperature 2 is equal to 450 Kelvin. So essentially what we're trying to find is to find the work boundary between 1 and 2 using our polytropic equation. So we know that we have a polytropic equation equal to P1V1 to the 1.4 is equal to P2V2 to the 1.4. And we know that we have to find work boundary is equal to the integral from 1 to 2 of PdV. Okay, that's our definition. And then the equation we're going to use is the polytropic equation for n is not equal to 1. And that polytropic equation is P2V2 minus P1V1 over 1 minus n. Now, there's two ways we can solve this. We can solve it using the long way or the short way. So let's look at the short way first. So the short way is to recognize that, and we had looked at this in the last section, in the last part of the module, we had looked that we can substitute, we can say that P1V1 is equal to MRT1 and P2V2 is equal to MRT2. And we had said if we can recognize that, so we recognize that. So I'll write this as like method 1. Okay, so this is method number 1. If we recognize that P1V1 is equal to MRT1 and P2V2 is equal to MRT2, we can then say that we can substitute these two for these two. And so we would be left with an equation that looks something like this. We would have work boundary is equal to MR times T2 minus T1 over 1 minus N. Okay? And we are given temperature 1 and temperature 2. We're also given mass. So we have this term. We have this term. We have mass. We have N. The only thing left to find is R. How do we find R? We find R from Appendix A1. So we go to Appendix A1, which is the first table in our appendix, and we go look for nitrogen, and we find that R is equal to 0.968. So the value is right here, 0.2968. So R is equal to 0.2968 kilojoules per kilogram Kelvin. So it's kilojoules per kilogram Kelvin. That's the unit. So now we can just plug in our values. So we have work boundary is equal to the mass, which is 5, multiplied by 0.2968, multiplied by 450 minus 250. The temperatures are already in Kelvin. And then 1 over 1 minus 1.4. And we get that this is equal to minus 742 kilojoules. And as expected, the work is done on the system. It's negative, so the work is being done on the system. Now, there's a second way we can solve this, and the second way is a little bit more complicated. And it relates to actually the first example we did in this section. So method number 2, which I wouldn't recommend for this type of problem, but you can still try, would be to say we have work boundary is equal to integral from 1 to 2 pdv, which is equal to P2 V2 minus P1 V1 over 1 minus n. And the second method would involve doing the same thing we did before. So it would involve saying, all right, we have P1 V1 to the 1.4 is equal to P2 V2 to the 1.4. And we also know that our ideal gas equation stands. So P1 V1 is equal to MRT1. P2 V2 is equal to MRT2. And from here, we would then find pressure 2 from our isentropic relations. So we would find pressure 2 using the following equation. T2 over T1 is equal to P2 over P1 to the power of n minus 1 over n. Once we find the pressure, we could then find V1 and V2. And we could then find V1 and V2 from our ideal gas equations. And I should write this as capital V1, capital V1. So then you would find V1, V2 from these equations here, because we have the temperature and now we have both pressures. And then you would plug V1 and V2 and P2 and P1 into the actual equation. You can see that if you have the temperature at both steps, it makes it a lot easier to just use the first methodology, just substituting for MRT in our work boundary equation. Okay, so just two different methods of doing this problem. Now the next problem we're going to do is a little bit of a special case, and we're going to be looking at what that means. So then I'm going to copy over the next problem from our handout, and this will be the last problem for this section. Okay, so we're told that a piston cylinder device initially contains 0.4 kilograms of nitrogen gas at 160 kilopascals and 140 degrees Celsius. We are now told that the nitrogen is now expanded isothermally to a pressure of 100 kilopascals. Okay, so what does isothermally mean? So we're told that this is isothermally to a pressure. Isothermally means that temperature does not change. And if temperature does not change, we have a new type of system and we know the final temperature as well. So we can also make an assumption here. Nitrogen is an ideal gas. Okay, so we know nitrogen is an ideal gas. Now for this problem, we can't really say it's a polytropic process because it doesn't really tell us if it's a polytropic process. We have no real information at this point. So let's just keep going with our problem. And our problem says to determine the boundary work during this process. So what we need to find is work boundary. And so the first thing we're going to do, as usual, is to state 1 and state 2. And so state 1 is going to have a mass of 0.4 kilograms. We know that state 2 is going to have that same mass because we have a piston cylinder device once again. And we have a pressure 1 of 160 kilopascals. And temperature 1, which is equal to 140 degrees Celsius, which can be converted to Kelvin, but let's leave it in Celsius for now. But we can add 273 if we wanted to have it in Kelvin, which would be 413 Kelvin. So let's write it as Kelvin, just so we have the conversion already. We're also told that pressure 2 is equal to 100 kilopascal. And since it is expanded isothermally, we know that temperature 2 did not change. There's an isothermal change, so there's no change in temperature. So temperature 2 is equal to 413 Kelvin. We also know that nitrogen, we just looked it up, we know that nitrogen has 0.2968 kilojoules per kilogram Kelvin as its gas constant. And I'm writing this down right now because I know we're going to have to use it, but we could use it later if needed. So how are we going to try and solve this problem? So we need to find the work boundary, which means that we need to find probably pressure and volume. We already have pressures, so we're going to have to find volume. So let's try and find volume first and then try and figure out how we can even do this problem because we don't really know if it's a polytropic process or not yet. So first things we're going to do is we're going to say, all right, let's look for the volume so that we have all the information we need. Let's look for the volume here, and let's look for the volume here so that we can define our state correctly. And the volume on the right should be volume 2. Okay, so how do we find volume? We know we can assume ideal gas, so we can say that P1V1 is equal to MRT1, and we know that P2V2 is equal to MRT2. And from this, we can now say, let's rearrange it to find volume. So V1 is just equal to MRT1 over P1. And if you do the math for this, you'll get that this is equal to 0.3064 meters cubed. And V2 would be equal to and let me just show you actually working it out with V2 just to show you how the units cancel out. So we would have 0.4 kilograms multiplied by 0.2968 2968 kilojoules per kilogram Kelvin multiplied by 413 Kelvin divided by 100 kilopascals. So we can see that the kilograms cancel out. Okay, so the kilogram here and the kilogram here cancel out. The Kelvin cancels out. And then we have kilojoules divided by kilopascal. And essentially this cancels and this cancels. The little kilo cancels. And we're left with cubic meters. So we have 0.4903 meters cubed. Okay, so we can see how if we use kilopascals, we have to use kilojoules at the top. And we get a volume of 0.4903. So now that we have volume, we're still at a crossroads as to how to find work boundary. Well, the isothermal process, so an isothermal process is actually a special case of polytropic. So if you ever see that you have an isothermal process, you can assume that it is a special case of a polytropic with n is equal to 1. And the reason is the following. So let's look at the polytropic equation. And let's write just PV, not P1V1. So PV to the n is equal to a constant. Okay, that's our polytropic. And we're told that this isothermal is a special case of the polytropic. But let's try and understand why. So we can also write that P1V1 to the n is equal to P2V2 to the n. Okay, we know that from our polytropic rule. Now, because we have an isothermal process, we also know that temperature 1 is equal to temperature 2. So what happens if we write our ideal gas law out? We have P1V1 is equal to MRT1 and P2V2 is equal to MRT2. We know here that T1 is equal to T2. What happens to the right side of the equation? If temperature is the same, we have that essentially P1V1 is equal to MRT and P2V2 is also equal to MRT. Okay, just a general temperature, which is T1 or T2. So we can just write MRT1 would be equal to P1V1, which is equal to P2V2. And so if we simplify this equation and just get rid of the MRT, we have that we just proved that in an isothermal process, P1V1 is equal to P2V2. Now let's compare this equation here with our polytropic equation. It looks exactly the same, except we have a power of n on both sides. Well, the power of n is just a power of 1. If we add a power of 1 to our ideal gas equation, and the fact that they're equal when there's an isothermal process, we now have a polytropic process with n is equal to 1. So this is the proof of why an isothermal process is actually a polytropic process with n is equal to 1. So we can say this is a polytropic process. So moving on from that, we can now solve the problem. We know that for n is equal to 1, Now that we know that it's a polytropic process, our work boundary is equal to P1 V1 times ln of V2 over V1. So we still had to find volume 2 and volume 1, so that's great. We already have them. And we now have that this is equal to 160 kilopascals multiplied by 0.3064, which is our volume, meters cubed, multiplied by ln times 0.4903 over 0.3064, which is equal to 23 kilojoules. And we can say that work boundary is now positive, and this should be 23, not 2. 23 kilojoules. And we can say that work was done by the system. Work is positive. Okay, so we have work done by the system because we had an expansion. Okay, so this concludes part 3 of module 3, and this is where we stop our material that will be on quiz number 2. So anything before this will be on quiz number 2. Anything after this will be included on further examinations, such as the midterm. So we'll stop part 3 now, and we'll go to part 4, where we introduce the first law of thermodynamics for closed systems,